Welcome back to the third tutorial on computer vision, going from knowing the fundamentals to being knowledgeable in this domain. So in this third tutorial, we are going to cover in depth of CNN. So if we quickly take a look at what we've covered till now, so we've covered the basic image classification with neural network, convolutional neural networks, and now this is the third tutorial, more in-depth convolutional neural networks. And then finally, the data augmentation. So keep in mind, this data augmentation is a continuation of the third tutorial, the more in-depth convolutional neural network. So where we've left off in the third tutorial, we are going to continue with the fourth by showing you guys the different process that is involved in data augmentation and why it is even needed in the first place. Alright, so let's get quickly started with the third tutorial. So let me go to that slide. Alright, so yes, so in this third tutorial, it is the more in-depth CNN with custom dataset. So this is a much more comprehensive tutorial compared to the first and the second one. So in this tutorial, we are going to download and create. We're going to. So in this tutorial, we are going to use a custom data set that we'll download from the internet, extract it, and then visualize it. So that is what the first step talks about. And then, of course, with all the data sets, we need to pre-process the data set. And this time, we are also going to optimize the performance of the data set. So we'll see what that is. So we're going to use something called as AutoTune by the TensorFlow API. And we're also going to look at standardizing the data. So we're going to talk about all these pre-process and optimizing the dataset pipeline. This is quite crucial. Now it might not make much sense to use it, but however, knowing this and keeping this in your arsenal is highly important, because optimizing the data set, the way your program fetches the data set from your non-volatile memory, that is your hard disk, and then caches that data and then puts it into your volatile memory, is highly crucial, because this will typically reduce the time that it takes to train the model, basically. Because if you are getting the data set in the cache, it does not have to look at the hard disk. It can just look at the cache memory and then just fetch it from there. So optimizing this pipeline, the fetching of data set is quite crucial, especially if you're dealing with huge amounts of data sets of the order of 50 GB and above, right? So it completely makes sense to use these optimization pipelines. And then the third step is creating, compiling, and training the model. So in this, of course, we need to set up the model layers, sequential layers, and then create the CNN pipeline, that is your conv2D, your max pooling layers. And then finally, we're going to add some dense layers and the output layer. And then we'll train the model and then see how well it is performing on the training and the validation. Like I've already told you guys, the accuracy metric should be measured on the validation or on the test data more than compared to your training set. So we're going to do that, and then we're going to go with the next set of topic, that is the data augmentation. So however, that is for an entire complete new video. I'm not going to talk about that right now, but that is when data augmentation comes in. We'll see when we plot the results in the visualization step. We'll see that it's not going to perform all that well, and then we'll see why that happens and how we can go about it. And that's where the data augmentation comes into picture. All right, so let's get started off. I've already opened up my Jupyter notebook, so that's the third tutorial. So I'll just create a new Python Jupyter notebook, and then I'm going to call it more in-depth CNN. All right, so let's get started. Now, of course, the first and foremost thing is to import the libraries. So let me just copy paste so that let's not waste time. Let me just quickly go through the imports. Of course, matplotlib for plotting different images, numerical Python for data or array manipulation, OS for operating system for libraries and all that stuff, PIL for plotting the images from a particular directory, right? And then TensorFlow, of course. And then we have Keras. Of course, we do not need this, but tf.keras layers for adding different layers in the sequential API, and then of course the sequential API itself. So let me just quickly go ahead and run that. Cool, it ran now. Let's understand how the data is going to look like, or the data directory is going to look like. So we are going to download a data set called as flower photo from the Google storage or the Google Cloud. That basically contains of different types of flowers: daisy, dandelion, roses, sunflowers, and tulips, right? So inside of this folder, so it has multiple folders for each classes. So every folder represents its class. So for example, everything inside roses will be the flowers of roses. I'll show you how that works once we have downloaded the data set. All right. Okay. Now let me just quickly copy paste the downloading dataset code. So of course we'll be using pathlib to handle the path library. I'll show you where exactly it comes into the picture. Now we need a URL to download the flower photo from. So this is the URL. Don't worry, this URL will be shared to you guys in the resource section, right? So this is where you just copy paste the URL and set it to dataset URL, and we have a utility function from TensorFlow that is tf.keras.utils.getFile. So if I come and shift tab on this, so the docstring says that downloads a file from URL if not already in cache. So what it does is, given a URL, it will download from that URL. Now if it already exists in the cache, then it will not. Now how does it know it is in the cache or not? So it just checks this directory, the home directory followed by .keras. This is a hidden directory, so if you're looking at it, you need to make sure that you set show hidden files. How do I know it's a hidden directory? Because it has a dot before the name of the folder. So anything that has a dot, any folder that starts with a dot is hidden by default. So that's how the Linux operating system interprets. So, and inside of the Keras, it'll check inside a subdirectory called datasets, and then whatever we pass in as the name of the dataset gets replaced. And then this dataset directory would be, or data directory would be passed to pathlib.path. I'll quickly, later I'll talk about why we are doing this. So let me, oops. Oh, okay, I see why. I've given double equals. I should just say single equals. So it is downloading from the dataset, downloading the data from the specified URL. So thanks to the keras.utils.get file, right, it is downloading for us. So let that download. Meanwhile, let's see the image count. So how many number of images there exists in that particular directory. So we say that is where the pathlib also comes into picture. So to know the length, we need to pass in an iterable, right? So that's why to pass in an iterable, I'm just going to convert it to a list so that it can be an iterable, and then I'm going to say data directory dot globe. So before we do that, now that's done. Now it is downloaded and extracted. Let's check out data directory dot globe, right? And then I'm going to pass in. So what does this globe do? The globe basically iterates over the subtree and yields all existing files of any kind, including directories, so matching the given relative pattern. So that's what I'm going to do here. So it basically goes through the directory and yields all the files that matches a particular pattern, So the pattern we give is JPG. So once after it's extracted inside of these folders, every image is of the type JPG, and we don't care what the name of the file is. We just want everything that the after which there is a JPG extension. So the file name .jpg. So if I give enter, it is a generator, you can see, and since it's a generator, we can just convert it to a list, and then have the list taken care of with the length. So let me just call in the same regular expression or pattern matching JPG. All right, so the image count came to be 3670. So now let's plot few images. So let's say I wanted images of roses, so I'm going to say list of data directory dot globe. Like I said, globe does a regular expression matching, so I want the directory roses and then everything inside of those directory. Now since it's a list, it'll come out as a list. Now we can just start plotting that image. PIL dot image, image dot open, and then we can call the roses of 0. So that will print the first rose image. Now let's say if I did 2, another rose image. Yeah, these are pretty beautiful rose images. So we see there are diverse different rose images that are there. Now if we wanted for tulips, it's pretty much the same. We just convert that to a list and then call the glob and then say tulips, TULIPS, then everything inside of that, 0 or 1, and then PIL dot image dot open, so tulips of whatever. So yeah, you get the idea, right? Now let's load the data set. Now I'm going to load the data set, or you know what, I'm just going to make it as a heading, then call it as load the data set. Now in loading the data set, we're going to create the data set. Create the data set into train test split. That's what we'll do, the TVS. We won't do the train test split, we'll do TVS, train validation split. So that is TVS, train validation split. So we'll just say train data set is equal to df dot keras dot utils dot image data set from directory. So what this function does is, if I do shift tab, it says generates a tf.data.dataset object from image files in a directory. So if we give a directory, right, which contains image files, now like I said, now whatever we've set up with the data directory is perfectly matching the data or the input that the image flow from directory is asking for, or image data set from directory. So all we should do is we can just pass in the data directory, data directory, and then say validation split equal to. Now if you don't know where all this is coming from, you can just check it out, check the doc strings and different arguments it takes. So we say validation split, so we want 0.2% of the entire data set to go to validation, right? So sorry, 0.2, so that is 20%, and then we call the subset as the training. Now if you do shift tab and look into the docs, what subset means is, so one-off training or validation. So it could be a training or it could be validation, only used if validation split is set. So if you're using subset, you need to make sure that the validation split is set. Like in this case we have set the validation split, and then we say the subset to training, right? And then set the seed. So we'll set the seed to 1, 2, 3, so that if you want the same reproducibility, you get the same reproducibility. Now let's quickly check the docstring for seeds so that you understand what that is. Optional, it's an optional field. Random seed for shuffling and transformations. So if you so basically this image data set from directory will automatically do some shuffling and do some transformations. So if you want the same reproducibility, so we set this same seed size, seed value, so that you and I have the same reproducibility. So we say image size is equal to image size comma image width. Now we haven't defined the image size and image width. Let's quickly define that. Image e size z comma image e size z equal to 180 comma 180. So we set the image size and image width to be equal to 180 comma 180. So with that being said, we can set the batch size. So let's set the batch size as well. So batch size equal to 32. So with the batch size equal to batch size. Now if you don't know what batch size means, let's quickly check it out. So size of batches of data, default is 32. If none, the data will not be batched. So basically what batch size means is, for since we have like 3000 plus images, right, so we don't want to send one by one or all the images together. So what we do is, instead we create a batch of those data. So in this case 32, so that means at one shot we'll be passing 32 different images, so that the model learns from those 32 images, and then the next set we'll pass the next set of images, so next 32 set of images. So that's how it is going to work. So that's why we set the batch size to 32. Right, now if I image, oh my bad, image width. Now it says found 3670, that should match to the image count, yes. So belonging to 5 different classes. How does it know it belongs to 5 different classes? Because we are calling the function or the method image dataset from directory, right? So the directory has 5 different folders, and that's how it knows each directory name, or the directory itself as a class name. So that's how it knows there are 5 different classes. And since we did a 20% split for validation, off of those 3670, it is only using 2936. So if we do 0.2 into 3670, so that is so now we do 3670 minus, so you should get 2936, right? So this is how we ended up getting 2936. So you can change the validation split. However, it's advisable to, oh shit, okay, so you can do the validation split. Okay, so you can do the validation split of more than 0.2. However, it is advisable to keep more to your training data and then less for your validation split, because you need more data to train the model with, right? So that's one key tip to remember. And then we are going to say validation data set, or valds, is equal to, again, tf.keras dot utils dot image dataset from directory. Then we're going to say data directory itself, and then validation split is 0.2. Here we're going to do the exact opposite. So instead of instead of saying the subset to training, we say it validation. right? So this set of data will go to validation, and then seed equal to 123, and then image size is equal to, as a tuple, image size comma image width, right? And then the batch size equal to batch size. All right. Now, like I said, 0.2% of 3670 is 734. So much data is going for validation. And again, it says that it found 36705 files belonging to 5 different classes, amongst which 734 files are going for validation. Now, I hope that makes sense. Now, let's just get the class names. Now, how do we get the class names? So there is this function called from the train.ds based on the folders directory. It has a function called as a method called as class names. So it gives the different class names in the order in which it was received. See, daisy, dandelion, roses, sunflowers, and tulips. So it maintains the same order. So we can just say class names equal to that, right? And then this is helpful for visualization. So let's just visualize the data. Now this is the same code. So I'm not going to type it out again so that we don't take too much time. However, I just want to show you one cool thing using the train.ds variable. So so train.ds is basically tf.data.data set type. Now if I do the type on this, you see that is basically data.data set type, right? So since if it is of that type, I can basically do something, call a function called take, and then pass in 1. So what this does is it basically, since it comes in batch sizes, if I do take of 1, it passes the first batch, and if I do take of 2, it passes the second batch, so on and so forth. And this is a like a a generator type, so that I can pass in a for loop and then start querying the elements from the train.ds.take. So that is what this is doing. So take data set, this is of a take data set type element, which gives in the 180 by 180, right? And it's a 3, so 3 stands for the color, that's the shape. So that's what we are passing here. So every image gives you the images and the labels. So when I say train.ds.take, it gives that particular image and its corresponding label. So that's how it's going to work. And for I in range, of course, if I say 9, so I want 3 columns and 3 rows. So 3 columns, 3 rows, that's what this is doing. Add an axis to current figure or retrieve an existing axis. So that's what it is doing. And then imshow, of course, and then we just converting it to numpy and the uint type 8. And then we're giving the class names just like previous, right? So this is how the image looks, right? So this is how different images look. Now if you wanted to manually iterate over the data set, right, you could just print this, and you see it's of batch size 32. So batch size comes first, and then your height, width, and then your number of colors and the corresponding labels. So since the batch size of 32 means there are 32 different images, so its corresponding value is 32. So let me just say take of 1, so it should still be the same. If I do take of 2, it will still be the same because it is giving me another set of batches, but the data set won't stay the same. Now if I do take of 2 here, you get another set of images. You see that? So that's how it is working. Now a very crucial important aspect is, now where are we till now? So we've downloaded and we have visualized Now the next step is to optimize the dataset performance. So let's start optimizing dataset performance. So let me just change that to a heading. Okay. Now this is where the auto tune comes in. Auto tune equals tf dot data dot auto tune. So now we need to pass this auto tune to the data set that we have. So tf train data set. So in auto tune, what we are going to be performing is these are the two steps. So we perform the first thing is data set dot cache, and then data set data set dot prefetch. Now if you wanted to know more about what this does, we share the links. However, dataset.cache basically caches the elements in the dataset. It's that simple. That's it. It's not doing anything more, anything less. It just caches the elements in the dataset. So the first time the dataset is iterated over, its element will be cached either in the specified file or in memory. Subsequent iterations will use the cache data. Now, if you take an example, tf.data.dataset of range of 5 gives us 5 different values ranging from 0 to 5. Now, this is just a map operation that will take a lambda expression and then do x squared over all the values of the data set. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So that's how it works. Now, if you do dataset.cache, it will, for the first time, it will iterate through the dataset. However, the subsequent iterations, it will read from the cache itself. By doing this, we'll save a lot of time. It is not significantly visible in this example, but imagine a data set that consisted of 40 GB. Now, if you're able to cache like, let's say 2-3 GB of data, compared to fetching it every time from the disk, caching will make your performance a lot better. And the same thing goes with prefetch. So now for prefetch, let me just open that as well. So prefetch basically creates a data set that prefetches elements from this data set. So most data set input pipeline should end with a call to prefetch. So what this basically does is, for every data set you have and you call the prefetch with some value on it, it will prefetch the value from prefetch those elements from the data set, so that it is already there and you don't have to run it once it is required. It is like you're already giving something well in hand. That's the best example I can say. That's what prefetch is. Now if you wanted to learn more, we'll share you the links. You guys can check it out. They have a very good, very extensive documentation on these, so do feel free to check out. So that's what we'll do. So we'll set the cache on the data set, and then we'll do prefetch on the data set. So how do we do that? So we say train ds dot cache. That's it. And then we want to shuffle the data set, and then we call the prefetch. So do keep in mind that since this is a tf.data.dataset type, because that's how we can perform all these cache and prefetch, all those operations, it needs to be tf.data.dataset. We can call the prefetch on that as well after calling shuffle. And then we say buffer size. So how much to prefetch? That will leave to auto-tune. So auto-tune is is so amazing that it will automatically decide what is the value to be passed. So that's why we use auto-tune. So if we come to tf.data, and then we just search for auto-tune, right? So yes, better performance. or we can just come and Google this tf.data.autotune, then search for autotune. Yeah, so autotune will automatically determine how much to prefetch based on so many different factors. Uh, Now you can read the documentation on it because it's too much to cover in one particular video, right? So it's too much to cover. So you can see the different aspects that it considers uh, and see the different execution time with and without autotune. So that's why autotune is so important, so that we can just pass in the autotune class and it will automatically determine what is the best values to pass to prefetch. All right, now we have to do the same thing for validation dataset as well. So val data or valds is equal to valds.cache, oops, cas cache, and then we don't have to shuffle because it doesn't matter. Prefetch, and then the buffer size equal to autotune. All right, now if you come to the pipeline or the step by step as to what we are doing, I said we have to also pre-process the data, right? So let's do a little bit of pre-processing, that is rescaling or standardizing the data. Now we'll standard the data. Now, since the values of the data set, like I've spoken in the previous tutorials as well, since the RGB values of the data set or the images or of the values are in the range of 0 to 255, this is not really ideal, right? It's not really ideal because the model will give different importance to values more than 0. So if 10 has, if the value is 10, it thinks that 10 is more important than, let's say, 2 or 3. So that's why, to reduce this ambiguity, we have to standardize the values to be between 0 to 1. So it has to go from this to being 0 to 1. So 0 to 1. So how do we do that? We can use something called as TF, the rescaling from the layers. So we can do the normalization layers by basically what we do with standardization is basically normalization. So we can do that using the rescale operation. There are two ways of doing the rescale. However, I'm going to show you the best optimal method of doing the rescale, that is passing the rescale operation as a sequential layer itself. Now I'll show you how that works. Now, so in order to do that, let's start by creating the model. So this is a two-step combined to one step. So there are two different steps. That is, the first one is standardizing the data, right? Standardize the data and then creating models. Model layers. So you're going to pass the rescale operation as a layer itself. Now we can just start off model equals to, now this should be pretty straightforward, equal to sequential. There are two ways of doing this. We could say sequential and then keep saying model.add, or we can pass in as a list of layers. We can pass different layers inside of the list. So that's how we're going to do, and I like this way of doing it because everything will be easier. You don't have to call .add every time. This is what I like, but you guys can decide what you like. So we just now, like I said, to standardize, we'll rescale. So 1 point dot for divided by 255, and then of course we need to give the input shape because this is the first layer. So that is equal to So that is equal to image height by image width. I'm sorry, I think I gave a very wrong name. It should not be image size, it should be image height. So do keep in mind. So image size refers to image size. Let me just make sure that you don't get confused. So here image size is equal to image height. And what else? The color, the channel color. So here it says a pre-processing layer which rescales the input values to new range. Now if you check out the documentation, it says to rescale an input of the form 0 to 255 to 0 to 1, you should pass 1 divided by 255. So that's exactly what we want, right? So we want the image from 0 to 255 to go from 0 to 1. And to do that, we just do the rescaling operation by passing 1 divided by 255. And dot is just to make sure it's a floating division and it's not an integer division. And then after that, everything remains the same. You start by calling layers dot conv2d, the convolution operation, right? So we have 16 different convolution operations. And what was the second item? So that is filters, or the kernel size. So we could pass in as a tuple like this, 3 comma 3, but even if you pass in as this, it's still fine. So only one value. TensorFlow understands that means 3 comma 3. And then we set the padding to same. Right, and then of course we have the activation to be ReLU. And then next we have layers dot, what is the next layer? It's the max pooling 2D or max pool 2D, if you guessed it right. And then the default value is 2 by 2, so you don't have to say 2 by 2 like this. If you just leave it to default, TensorFlow understands that I'm looking for a 2 by 2 max pooling operation. So layers dot conv2d. Now like I said, we increase it with a factor of 2, so 16, 32, 64, 128, so on and so forth. So we'll add 4 different convolution layers, right? So 3, and then padding to be the same. Oops. And then activation to be ReLU. Now you see, just typing the same thing is quite annoying. So what I'm going to do is layers dot max pool 2D, right? So I'm just going to copy this, and then I'm going to paste it twice. Make sure you don't give any indentation. I mean, this is fine since it's inside of a list, but you know how Python works, right? Indentation is very crucial. So I just do 64 and just 128. So, and then I'll remove the padding for the last layer. It's not needed because it's the last layer, and I of course don't want max pool 2D. I don't know why I always make this mistake of 1287. Right? And then what is the next layer that we need to pass? We need to pass the dense layers, and before that we need to flatten, right? So don't forget to flatten. And then we say layers dot dense. So of course we want 128 different layers because the last convolution operation ended with 128 different layers. So 128 here is the number of dense units, and then of course we want activation to be again ReLU, right? And then the last layer, that is the output layer, so we say layers dot dense, and this depends on the number of classes. So if you know the number of classes, we just say length of class names. So if you remember the class names, it was basically a list, right? Now you can call the length operation on the list. That gives you Now let me just quickly do that. Length of class names should give you 5, as there are 5 different classes or 5 different libraries, sorry, directories. Now, all right, so we just created a model. Now let's look at the model.summary. Now the first would be a rescaling operation, so that's why there are no parameters. The second is the convolution operation after the rescaling, so there's no change in the dimension from rescaling to convolution, as the dimension itself does not get changed, only the values get changed, right? And then we have the max pooling. Like I said, it reduces the image size into half, and then another convolution operation, another max pooling, so it is reduced by half. If you remember the second tutorial, I'm sure you might remember the formula. So that is image size minus the kernel divided by stride plus 1. So if you apply those formula, you will know how you're getting these values. And then finally we flatten it, so it's 20 times 20 times 128, so that'll be 20 times 20 times 128, so that'll be 51,200, a single unit, a vector, and then that vector is passed to a dense layer, and then finally an output layer. So with that being said, we're ready to, what is the next step? The next step is to compile the model, and then train the model. So if you see, we standardized and created the model in one single step, right? Instead of creating 2 different steps for it, we just made it in a one single step. So I feel this is the best way to do it, but there are different ways that you can check it out and use the one that you feel the best for you. So now we have to compile the model, so model.compile. Now of course we have to pass different parameters. So optimizer is of course Adam, right? And then loss equal to tf dot keras dot losses dot, of course this is a sparse categorical cross entropy, and then let's not forget from logits to set to true. Then we want the metrics to be the accuracy, and then we will call, we'll set the history equal to model.fit on what? On trained ES. Right, and then the validation data is equal to valds, and then epochs, let's run it for 28 epochs. Now for the moment of truth, all right, so it did not throw any error. Now let's see, it is running, it's fairly quick. So let's see the accuracy. Wow, it started from 44% to now it's already 85%. Okay, it's going to 100%. Whoa, it's awesome, right? It's going to 100%. Please don't be fooled. This is on the accuracy is on the test data, sorry, on the training data, especially since you are passing in as batches. So don't be fooled. This is not the metrics that we want. We want to see the validation accuracy, so that will be way less. You see that it is about 66%. So this is a clear indication of something called as overfitting. Now this is where the data augmentation comes into picture, and using data augmentation we can remove this state of overfitting, and that will take it up in the next tutorial. So till here I hope you guys understood. So we've covered everything from downloading the data set, pre-processing and optimizing the performance using the auto-tune, and then of course cache and the prefetch operations, and then creating, compiling and training. So we combined the pre-process operation and creating the model in one step, then we compiled and trained the model. Next is we'll visualize the model performance since we have tracked the history. All right, so it's a bit of code. I'll just copy paste that code because I don't want to waste too much time, but I will walk through the code. So history.history is basically a dictionary. Now history, now we have tracked the history.history. Now is basically a dictionary which contains different values or different keys. So if I say dot keys, oops, see it tracks different accuracies, right? So it has different metrics. So it has loss, accuracy, validation loss, and validation accuracy. So that's how we can use these values to plot the graph. So we'll say accuracy is history.history of accuracy key, and the val accuracy is validation accuracy key. Loss is loss key, and validation loss is validation loss, right? And then epochs equal to range of epochs. Now this is not set, so range of 28. So it's a fixed size of 8 by 8, and then subplot. So 1, 2, 1. Now we're just plotting the different metrics, the training accuracy, validation accuracy, and the legend we want it low, right, so that it does not interfere with the graph. The same thing we'll do for the training and the validation loss. This is the training accuracy and validation accuracy. This is the training loss and validation loss, and then we just plot it. Now you see, ideally the training and validation accuracy should have gone up. The training went up, however the validation kind of scrambled over at 0.7. Now if you look at the loss increased over time, validation loss increased over time, whereas the training loss reduced over time. So now this sorry, not over time, over epochs. The x-axis is epochs and y-axis is the accuracy or the metrics that we are looking for. So ideally this is this is typically a best example of overfitting. So we don't want to get ourselves in such a situation where the training accuracy is reaching all the way to 100%, and then the validation accuracy is just surfacing somewhere around 60-70%. That is not what we want. So in order to mitigate this issue, we are going to do the we're going to address what overfitting is, and then we're going to tackle on how we can solve these overfitting issues, and that's where the data augmentation comes into picture. We'll add different data augmentation layers, and then we'll also add something called as dropout layers, regularization layers, and then we train it, and then we'll see the difference. All right, so that is the tutorial for this the third more in-depth CNN. So this is where we'll end today, and in the next tutorial we'll see how we can address the issues that are arisen by overfitting. Thank you. Until then, have a great day.